Alright guys, welcome back. Previous video was about just generally how the periodic table came to be. Cool guy called Mendeleev came up with it. Organised, it's all in the last video, you get it. So we talked about generally why the shape is like it is. And yeah, the periods are the horizontal lines, and that's based on mass. So lightest to heaviest, left to right. And we talked about why they're in the certain groups they're in, the groups which are the vertical columns. And that Mendeleev said, I'm going to put all of the guys who act the same way, they have the same properties into the groups that they're in. So we know these guys all react with water violently. These guys all react with oxygen to make oxides, and we'll talk about that later, and they react with acids in the same way. These guys over here are all noble gases and turn their noses up at everybody, even their mates that are the same, won't react with anybody. So the question we now have is, why do they do that, right? We've got the table, we sort of know why it's organised the way it is. Why do they act that way? Why do all the noble gases, why are they unreactive? Why are they boring? Why do they do nothing? Why is it that these guys are so cool and explode in water? Why do they do what they do? And Mendeleev didn't have the answer to that. He organised them based on his observations, but he couldn't explain why. What I want to show you now is, previous videos we talked about the atom and where the electrons live, right? In those shells. 2 in the first shell, 8 in the second shell, 18 in the third shell. I want to now, scientists often, we grab bits of information from here and there and see if there's any relationship. We're going to look for a relationship now between electron configurations and this periodic table, right? That Mendeleev made, and this is the coolest bit, you've got to realise science is cool. He made this without any idea of electron configurations. You may or may not be able to see it, what I'm about to do on the board. Okay, so you might have to have this PowerPoint up in front of you on a computer and click with me as you go, alright? So what we're going to do now is going to put over the electron configurations of each of these elements on top of on top of them, just so we can see what their electron configurations look like as a big part of the periodic table. Is there any patterns? We're looking for patterns, right? Scientists do that all the time. So hydrogen, we're going to start number 1. We're going to go left to right, we're going to look at their electron configurations. So I'm going to click it. You probably aren't going to be able to see it very well, but we know that hydrogen has 1 electron. That's it, in the first shell. So its electron configuration is 1. I'm going to move across here. Helium, his electron configuration is 2. 2 in the first shell. All right. Then we go to lithium. We're into period 2 now. Lithium, the first shell is full. All right, so hydrogen, helium, we've filled the first shell. We now got to go to lithium. We've got an extra proton. Remember, every single time we go to a new element, we add a proton. 1 proton, 2 protons. Lithium is 3. So his electron configuration is 2, 1. 3 protons, 3 electrons, and the last electron added has to go into that second shell. So it's 2, 1. Now we can flow across the second period pretty quickly. 2, 2 for beryllium. 2, 3, 2, 4, you get the picture, 2, 5, 2, 6, 2, 7, and 2, 8. That we've done period 2. That's the electron configurations for the period 2 elements. Now, one important side note that I have not made yet, and I probably should have made it in earlier videos. On the PowerPoint that you can probably see better on your own computer, I've highlighted numbers in red as part of the electron configurations. Those numbers that I've highlighted red, they represent, or they highlight to us, just as a reminder, that those are the electrons in the outermost shell. They're the ones furthest, typically, from the nucleus. Okay? So if they're further from the nucleus, I've highlighted them red. They're in the outer shell. And they're called valence electrons. Okay? So they're really important. We need to know about them. Okay? So they're called valence electrons. Electrons that are in the outer shell of an atom. Okay? So, for example, lithium has 1 valence electron. He has 2 in the inside shell. Think of it like layers of onions, right? Ogres are like onions, right? Shrek, whatever. There's layers, right? These shells are layers. The first layer is filled. We've got 2 electrons in lithium they're in the inner shell. Then we've got 1 electron in the outer shell. That's the valence electron. Then the second beryllium has 2 electrons in the outer shell. So he's got 2 valence electrons. All the way over to, say, the noble gas, neon, who has 8 electrons in his outer shell. He actually has a full outer shell. There is no more room at the inn, right? The house is full. If we have another electron added, where's the next electron going to go? He's going to be sodium. He's going to go to the next shell, shell number 3. Okay, and sodium will therefore have 1 valence electron again. So here we go. So we can do the third column. So we go down to here, sodium 2, 8. comma 1. So we've got one extra electron than we had before over at neon. And the same process occurs. Now can you see a pattern? Look at your computer. Can you see a pattern in the groups? Have a look for a pattern in the groups. Why? And remember, this is the coolest part, man, that Mendeleev didn't know these numbers. He made these without knowing that these numbers existed. He didn't know about electrons like this. He had no idea. I think you can see it, right? How cool is it? All of the elements in group 1, the alkyl metals, have one valence electron. Now, here's a hint. If you go all the way down, I'll just keep rolling pretty quickly. If you go down through all of that group 1, yes, they have all different numbers of electrons because they've all got different numbers of protons. But the thing that stays the same for all of these guys in group 1 is they all have one valence electron in the outermost shell. Every single one of them has got one electron in the outermost shell. The outermost shell might only be at shell number 2 or 3 or 4 or 5 or 6, but they all have one in the outer shell. Pretty cool. Mendeleev didn't know this and he made it like this. How cool is that? That just fits perfectly. In group 2, they all have two valence electrons. We jump across. We're going to ignore the transition metals for now. They're a bit trickier. Group 3 or 13. I'm going to say group 3 for now because 3, there's a little pattern here that's forming, right? Group 3 has 3 valence electrons, no matter what element you're talking about. Group 4 has 4 valence electrons, no matter what element you're talking about. Group 5, 6, 7, 7, and group 8 all has 8. So all of these noble gases have full outer shells. Their shell is full, okay? Doesn't matter what element you are, the further down you go, they all have 8. Now you've got to realise that this is cool, right? Mendeleev, years before, came up with this pattern, this periodic table, and then we overlay our electron configurations that we've now worked out. And we see that these numbers fit perfectly. There's this pattern that arises. If you've got group 1, you've got one valence electron, no matter what element you are. If you've got group 2, you've got 2, etc. And remember how Mendeleev made these groups. He put all of these guys into group 1 because they all exploded in water. So here's the question. Is a logical inference, right? A logical conclusion to be made here is that if an element has one valence electron in its outer shell, it's really reactive. So that tells me as a scientist, go, man, electron configurations actually impact, they're one of the big things that impact how an atom will interact with other atoms, how it will react. Because look at the noble gases. All of these guys, remember, they turn their nose up at everybody, right? They don't react with anyone. And yet, and why is that the case? Well, we can deduce why it's the case now. It's because they all have 8 electrons in their outer shells. Their shells are full. It appears like, it's like their happy place, right? You watch Happy Gilmore, you go to your happy place. It looks like these noble gases are in their happy place. They've got 8 electrons in their outer shell. They're full. The house is full. They seem happy. They're stable. In chemistry we'll say they're stable. Their energy is low. It's like you guys have gone to bed and had a sleep. You're stable there, right? You're not going to hurt yourself. You don't have a whole lot of energy. You're having a sleep. You're pretty chilled, right? It's like you guys have gone to bed. These guys are happy. They're stable. They've got a full outer shell. It looks like the electron configuration controls or has a big impact on the chemical properties of an atom, which is really cool because you can make predictions now based on, you don't even have to memorize this stuff. You have the periodic table. You say, tell me an element, Mr. Kippen. I go sodium. You go 2, 8, 1. You go, he's got one valence electron. He's going to be super reactive. I just know it. Really cool. So that pattern there is really important to remember. The other little trick is, if you want to know how many valence electrons, the ones in the outer shell, an element has, you just got to check the group number. Skip the middle, right? Group 1, 1 valence electron. Group 2, 2 valence electrons. Group 3, or 13, 3, 4, 5, 6, 7, and 8 valence electrons. Really cool. Okay? So there's the pattern that Mendeleev didn't know about, but that existed because he did such good work with his science to organise the groups. So the summary of this little video is electron configurations are really, really important, and that the valence shell, the outermost shell, is most important to controlling an element's chemical or particularly chemical properties. So we've sort of answered our question with sodium, right? We've at least partially there. Why is sodium so reactive? Well, part of the answer is that because it has one valence electron in its outer shell. And it seems like it's not stable with one electron. So something's going to happen to that electron when we throw it into water. And the other thing is, I'll push you a little bit here and go, well, what does it want to be like? What are all elements trying to, what is this, if this is an unstable configuration with one electron in the outer shell, what's a stable configuration? Where are people happy? It looks like the noble gases are the answers. They're called the rock stars, right? Looks like every element wants to be like a noble gas, wants to have the same configuration of electrons as a noble gas. They want to have a full outer shell. That seems to make them more stable. So what do you think sodium does when you throw it in the water? He's got one little valence electron out in the outermost shell. What might he do? We'll leave that up to you. We'll come back to that. Cool.